Hello everyone. With the aim to reduce wastage of water in agriculture as well as in home gardening system, me and my team bring forth the idea of a smart sprinkler system which works on real-time analysis with on-premise implementation of the system using machine learning model that allows automatic integration of the model on the system as well as automatic watering of the plants based on the climatic conditions as well as the weather condition. And not only that, it also allows for the user to control the system, pausing the real-time analysis as per user intervention using a mobile app. Not only this, but we also propose a proper report format which allows the user to get notified about the total amount of water he has saved in this system. And not only that, he also gets to know how much he can save in the next time whenever he uses the system as well, with the motive to maintain a sustainable environment and reduce the wastage of water due to overwatering of plants. We bring forth this system, and each and every module of this system will be explained in great details by my team in the following part of the video.
Hello everyone, I'm Pallav Gupta and I'll be taking you through the hardware model of our smart sprinkler system. In the current smart sprinkler system, we have used the following components as you can see has been highlighted by me. So moving ahead, we are first going to start with the board by using the ESP32 Pro. As you can see the circuit diagram that we have attached. We have also used density humidity temperature sensor DHT11 as you can see in the pin diagram. We have used a soil moisture sensor to count the moisture in the soil and also the LDR pin to detect the light intensity. These serve as the parameters and the actuator is the motor that is placed in place of the pump. We have also used a buzzer that basically tells us whenever the prediction is starting after the user intervention, following other soil components. Thank you.
Greetings, I am Meena Chattopadhyay and I will be explaining about the data collection and the machine learning model. So as you can see, it is the Tinkercad simulation of the hardware that we have built. We have made use of the soil moisture sensor, DHT sensor which collects temperature and humidity, and the LDR sensor which is used for collecting light intensity. This is the hardware simulation and we have followed the same for building the actual hardware and collecting the data. As you can see, we have collected the data through ThingSpeak. And the ThingSpeak part, you can see there are four parameters: temperature, humidity, soil moisture, and intensity. So we have collected the data by simulating various conditions in the lab. So temperature, we have collected around 2,500 data points by simulating the different environments, light intensity, and changing different parameters like soil moisture, temperature, humidity, and light intensity. And also what we have noticed that while exporting the data, there were some null values and the missing values. So for that, we have also taken data pre-processing and data cleaning techniques where we have replaced the null values and the missing values by taking the mean of that column, so that we don't have any null or missing values in the columns. And also we have removed the date time and the ID field. And also we have used an API to collect further data so that we can make our data set large and our model to be precise and accurate. So we have collected around 7,500 data points from weather API, such that it covers all the ranges of temperature starting from 15 degrees Celsius to 36, 38 degrees Celsius. And also we have collected humidity and the soil moisture using the same API, and we have concatenated both the data sets to make a combined data set of around 10,000 data points. So and also we have also changed the light intensity. Light intensity comes in the form of numerical values. So we have converted it to dim, dark, and bright as respectively, depending upon the light intensity values that we are getting. And finally we get a complete data set with no null values and a complete data set for training the model. And also we have used a weighted average method to assign weights to every parameter of the data set. So soil moisture has been assigned the maximum amount of weight, and temperature and humidity have assigned the equal weights, and intensity the lowest one. So based upon these values, we have calculated a weighted average, as you can see in the Excel sheet, that we have the weighted average for each of the columns. And also we have made a label for the sprinkler state. If the sprinkler state is 0, it means that the sprinkler is off, and if it is 1, it means the sprinkler is on. So after, you can see the completed dataset with all the weighted average, sprinkler state, and all the 4 parameters that will be used for training the model. And now coming to the machine learning model part, we have made use of the random forest classifier to classify and predict the state of the sprinkler, whether it will be on or off. So based upon the four parameters, we have trained it, and taking consideration of the weighted average as well. So we can find the accuracy is really high, around 99%. And here's the confusion matrix for the same. And also we are collecting real time data, so that it collects the real time data from the environment and predicts it then and there. And also we have made this on premise, that it runs on the board, so that it can be done on different kind of boards. So we have converted this ML model, which was in the TF Lite format, to a pickle format. This has been done so that it can be ease of conversion and the structure of the header file that we'll be building soon. So as we convert it to the pickle format, this has been converted to a .h file. So this .h file makes it and this .h file makes it very easy to run the ML model that we have built on an Arduino board. So we just have to call the header file, include the header file in the code, and just call the model and get the predictions from there. So the entire structure of the model is like, basically takes the data from the real-time data from the environment. It predicts the data on the using a random forest classifier, whether the sprinkler will be on or off, and then the prediction is given, and the sprinkler is controlled. So this is all about the ML model, data collection, and the circuit design, the simulation that we have showed. And the next part will be handled later. Thank you.
Welcome back, guys. I am Pallav again. So we will discuss about the coding and the Blink part of the module. Now, what we have done here is we import the important libraries first. This includes the Wi-Fi library, the ThinkSpeak library for data collection, Blink library for real-time dashboards, and we set up the auth token and the template name and template ID. We also set up the Wi-Fi credentials that we have used here. Now moving ahead, these are the following pins where we connect our sensors: DHT pin to 33, soil moisture to 34, LDR to 32, LED to 5, and positive 27. We also initialize the output string so that whenever we are sending an alert message to the user, we can store everything in one go and send it as a whole. Now we're going to just initialize the DHT pin. And here, as we explained before, the classification model has been called. This was called from the model.h, which was explained in the previous video. Now we also initialize certain variables like the overall saved water, the water that was saved, and the user, the amount of water that was saved over the whole period of time. So moving ahead, we have defined a classify function that does nothing but calls the above class and sends the particular values of temperature, humidity, moisture, and light intensity to the model and gets a classified output for it, and we return it. Now, basically, we have a setup function. Let me take it on to setup function. In setup function, we first initialize all the pin modes. Basically, everything is an input except the buzzer pin and the LED pin. LED pin can also is used interchangeably as the motor also. Okay. Now, moving ahead, we initialize a timer here, which was used in the blink. What it does is after every second, it initializes the send sensor function, which I will talk later on. Now, loop function is nothing but it sets up a connection with blink. Moving to send sensor function, since sensor function is going to do nothing but it's going to get the values, as you can see here. It's going to give us the output in the serial monitor, and it is going to classify the values. Now, after the classification is done, 1 represents that water is needed, 0 represents that the soil is moist, that means water is not needed. So we initialize a count variable that basically counts the number of seconds for which the sprinkler has been turned on at a delay of 1000. We initialize a false flag that basically means the sprinkler was not turned on, so there is no need to send extra alerts to the user. Now, basically, for the real-time analysis, we send the data over to the virtual pins that will be explained later on in the blink part. Basically, when it predicts that the water is needed, we basically switch on the sprinkler system and we keep on reading the sensors. Now, as we read the sensor, we keep on classifying it, and as soon as it reaches 0, we stop the sensor. So this is how the basic functionality of the smart sprinkler system is going to work. And once it is switched off, that means it is predicted as 0, the flag is turned true, and as it turns true, we initialize the string output and we send it to the user. Now, moving ahead, there is a additional functionality, that is the button that is present in a blink system, which I will talk later on. That adds the functionality of whenever the button is pressed, a value is sent over to us, and this value gets written to the LED pin or the motor pin. For example, if I switch on the button, my LED pin or the motor pin gets turned on. That means my sprinkler gets started. And after delay of 8000, that is 8 seconds approximately, I will hear a buzzer. What does that mean? That means basically that the user has turned on the sprinkler and now it is time for the classification to begin again. So after this function has completed, we go back to this particular line and we keep on repeating the whole scenario. This thing keeps on running until unless the board is turned on. Thank you. Now we'll be moving to the blink section.
Welcome back, guys. We'll discuss about the Blink dashboard that we have created for the mobile apps. The reason for creating Blink dashboard for the mobile apps is that it allows the connection to the sprinkler from anywhere at any time wherever you want to do it, and the distance it doesn't matter unless you're connected to the network. Now, in the particular dashboard, as you can see, we have shown four gauges, humidity, temperature, moisture, and light intensity, respectively. We also provide a switch that marks the on and off state of the sprinkler. This can be used by the user to turn it on or off on his behalf, and it also replicates the state of the sprinkler on based on the predictive real-time analysis that has been performed before. Now, as you can see, the data keeps on changing regularly based on the time period, and you also receive certain charts, as you can see, which will give you the time range of live 15 minutes, 1 hour, 6 hours, 1 day, 1 week, or 1 month. The particular variables have been color coded. For example, moisture represents cyan, humidity represents blue, temperature represents red, and light intensity represents yellow. For this ease to use and ease to access of the user. Moving ahead, we can also see how we have mapped the data streams into it. For example, humidity has been mapped to V naught, and here you can see the data streams like humidity to V naught, temperature to V1, light to V2, moisture to V3, and LED to V4. These are the virtual pins which have been written using the virtual light function in the code before. As you can see, temperature has been linked to V1, moisture, moisture is linked to the V3 pin, the light intensity is linked to the V2 pin, and we have a switch that is linked to the V4 pin that actually marks the state of the LED or the sprinkler system.
This is our working model, and as you can see, the soil sensor is currently placed in a wet soil. So based on this and our model, the prediction that we are receiving in our serial monitor is 0, as you can see there. And as a result for that, the sprinkler is currently switched off, and that can also be seen in our application. The sprinkler is switched off. Now, as we put the soil sensor in a dry soil, we can see the predicted class has changed to 1, indicating that the soil sensor is switched on. And now we can see the sprinkler is rotating as it is switched on, and in the application also it shows that the sprinkler is switched on. Now, as and when the water is given in the dry soil, as you can see right now, when we put water in it, the soil sensor detects the water, and as a result, the predicted class changes to 0. And as the predicted class changes to 0, the sprinkler switches off automatically. And in the application, we see that the sprinkler is switched off, and we get a report of the total water saved, water dispensed, and each and every thing, the report that shows here. We close the report, and we can see the sprinkler is switched off because it is placed here. So this is our automatic model. And now what happens is the user can control the sprinkler as per his own wish as well. So as you can see, the sprinkler is was switched off. As he switched it on, the sprinkler is switched on. The sprinkler goes on for some time. The buzzer sound indicates that real-time monitoring has started again, and as the soil sensor As the soil sensor is placed in wet soil, the predicted class was again showing to be 0, and the app also shows that the sprinkler is switched off. Now, the sprinkler is switched off. Now, when we put it in dry soil again, the predicted class again changes to 1. The sprinkler starts rotating on its own, and the app also shows that the sprinkler is on. Now user can again switch it off as per his own wish. The sprinkler switches off. The prediction stops for some time. And after some time, the buzzer sound indicates that the real-time prediction has started again. This real-time prediction shows that the predicted class is 1, indicating that the sprinkler is switched on, as it is seen. And in the application also, it is seen that the sprinkler is switched on. Similarly, again, when it is put inside wet soil, the sprinkler again automatically sees that it is wet soil. It stops, and we get the report as shown above previously. We can also see that the report that is generated is also sent to the user via email, and in the email section also he can see all his previous reports regarding the total amount of water he has saved and total amount of water he has used, predicting that he can save much more water as per his own use. Thank you.
So this was all about the project Smart Sprinkler System. And as you can see throughout the video, the scopes of this project is limitless, and it can be implemented at a lot of regions, including smart agriculture, as well as at your own homes. So imagine if you are outside and there is a sudden need to water your plants, you can do it from a remote place as well. Similarly, in smart agriculture, if there is a sudden rain or a sudden drought and you are not in a place to water them personally, you can do it via the smart sprinkler that we proposed. The future scope of improvements that can be seen is training the model on much more parameters, including like soil types, and making this sprinklers much more personalized to space. Also, we can invoke more renewable sources of energies, such as including solar power by invoking solar panels. These minor modifications will make the project much more robust as well as much more viable for environment. However, this project, as built by us, proposes a really good opportunity to save water and preserve the agriculture. Thank you.